This video tutorial will give you a brief introduction to the function of usage cases in Adapt Builder. And this is specific to Adapt Edge, which is the multi-story solver within Adapt Builder. Let's go ahead, and we're going to be using Adapt Builder version 2019 in this video. We are also going to want to make sure, if we select this arrow down button, that we turn on Adapt Edge. This will give us the ability to analyze a multi-story frame in multi-level mode in the program. I'm just going to switch over to RC mode. We're not going to have any post-tensioning in this instance. And let's go ahead, and we're going to just create a floor plate. I'm actually going to convert a CAD file, and then I'm going to extrapolate that vertically and create multiple levels or replicate that. And we're going to go ahead and import a DWG file. I'll navigate to the location of that file. We want to calibrate the file to scale this properly. And you can see it's prompting us here in the user prompt bar to enter the start point of the calibration. So I'll use my snap endpoint, and we'll just snap from point A to point B, or grid A to grid B, and enter a distance here of 20 feet. So once I've done that, I can now convert and transform these entities, if they're polygons, to actual components. So we'll take both slab regions. I've already selected one slab region. I'll select another. You'll notice it actually selects the grid line. So if I press Control and Tab at the same time, that will actually toggle back to the second polygon. Under Model, Transform, we're going to transform these to slabs. The next thing I'm going to do is just transform the core area, this area, and also the walls. So we'll do these individual walls first. I'll just press Control, select the walls throughout the model. And after selecting the walls, we can transform these to individual walls. I'll transform the openings. And then also we have a few beams here. The program will default to the beam depth. The beam width is based on the actual width of the polygon. I'll transform that over to beams. Again, if I double click, you'll see this will actually open the properties of the polygon. So if I select once and then press Tab, it will toggle back to the actual beam element that I had just transformed. And now I can go to properties and define a depth if needed here, or we can do that after we've finished using the CAD file, the DWG file, to transform. Okay, so the last thing we want to do is the columns. I don't want to spend a lot of time here just picking the columns manually. So if we double click on the column, we can see this belongs to tutorial level 1 column, and I can go over to home under the layer settings. I'm going to turn all layers off, and then I'm going to find that specific layer, tutorial 1 column. I'll just turn that layer on, and now I can window sweep and transform those into columns. Okay, so we have essentially our model built. If I want to go back and restore all of the other components that I built, I can either go to my default display, which is set under view settings, where here I can also turn on and view the different components. You can also view components from model. Under this visibility block, we could just select and toggle each component type off and on. Okay, and if I go to a side view, you'll note that by default we have, let me turn off these column. You can see these column entities. These are the polygons, so I'm going to turn that off. I'll go to visibility, group library. The CAD file that I imported is stored here under CAD group 1. It's partially on, given the fact that these polygons are turned on. I'll just go ahead and turn those off. So we have 3 default planes. The first elevated plane is really this current plane. I'm going to just go over here to Model, the Story Manager, and I'm going to add, I'll make these 12 feet, and I'll go ahead and just, we'll do this one 12 feet. I'll just add several additional planes in the structure. So we have 20 planes here. Once I've done that, I can take this and I can just replicate that vertically. Now I'm working in single level mode. So if I now go over to multi-level mode, you can see I see all of those planes that I added. I can copy this up vertically in either mode, but ultimately once we go to analyze the structure globally, we have to be in in multi-level mode. Okay, so I'm going to select these components. If I look at this in a 3D view, everything there is selected, and I'm just going to use modify vertical copy up. Here we're going to say 19 copies. And now we have this multi-story frame. If I go to visibility render, we can easily see the structure here. So what our purpose here really is to introduce the concept of usage cases in Adapt Builder. So right now, if I was to run this model globally for a set of lateral loads, maybe they're seismic loads in the x direction, the positive x, which aligns, let's say, with the positive x direction here, based on global orientation. The default usage case is called Uncracked, and that can be seen. Let me just select any component. I'm going to go back to single level. If I select this column, for example, and I go to Stiffness Modifier, the usage case is uncracked. And what this allows the user to do is to store separate or multiple usage profiles that contain different cracking factors for components in the same model. And the program can run and store the solution, meaning the reactions in columns and walls for those usage cases in the same model. So right now, for any component, if we go to the stiffness modifier property item, everything is set to uncracked, meaning the multiplier is 1. That cannot be edited. So if I go to analysis and under execute analysis or analysis options, you can see that when I run this model either in single level or global mode, in this case we're in single level, so we really would only be running that one level that's selected, which is current plane. The default set of cracking modifiers or stiffness modifiers is 1 because we're using uncracked. So what we're going to do is introduce and show how the user can introduce additional modifiers. We're going to add 3 modifier sets. These will be arbitrary. They're not necessarily related to what's recommended in any design code. It's just to show the user how you would go about doing this. If I double click on any component, I'll just click this wall, stiffness modifier. I'm going to select edit usage, and I'm going to add a usage. I'll call this cracked 70. I'll add another one called cracked 50. And here we have cracked, let's say 25. Now that defines the usage cases, which can then be assigned modifiers for any component. In this case, I've only selected one wall. So it would take the user quite a bit of time to go through every single component that they want to set modifiers to other than one and input the data in this field. In our example, what we're going to do is we're going to release the columns from any rotational stiffness, and then we're going to assign modifiers to the walls, and we're going to apply a lateral load, for example, in the x direction. And the objective might be, let's evaluate the drift under different cracking or under different stiffness profiles for the main lateral resisting system, which in this case would be our walls. So what I'll do is I'll go back to global mode, and if I go back to the 3D view, global, I want to select all of my walls. There's different ways I can do that. I can just select everything, and then when I go to modify selection, which allows me to apply the modifiers to a group of selected components, in this case walls, I could select stiffness and then set my modifiers here for all walls selected in this view. Another option, it would be to go to wall design, walls only. This at least allows you to see the walls. And one side note, by default the concrete material in this particular model is set to 4000 psi concrete. This is set to the default concrete 1. If you go to the result display settings under colorize, the program gives the user the ability to see and colorize walls based on thickness, material, and pure label. So this may be helpful in determining what concrete assignments you have for particular walls. And if I go to material, you can see everything is set here to concrete 1. So that's another feature of the program that may be helpful to the user. So again, we've isolated the walls. I could, again, window select. This is really similar to what I had just done The only difference is I'm not seeing anything else or selecting anything else. I could also just go back to default display and home, select by type, wall. Okay, and then we'll go to modify that selection. I'll go over here to wall, and now we can assign modifiers for these different usage cases that we've defined. And I'm just going to assign the modifier of 0.7, 0.5, and 0.25 on all entries. So we have moments about one axis, moment about two axis. Then we have vertical force, axial force, and also shear force in the strong plane of the wall. And we'll just modify those all now. Okay, so those have all been entered with the modifiers. These are assigned to all walls selected. So if I have multiple components selected, we can assign modifiers to those multiple components through this modify selection option. I'll select OK. Just to spot check, I could go and randomly select one of the walls, for example, and we can see the modification here to those usage cases. You could do the same for any component in the structure. If I wanted to modify the slabs in conjunction with the wall modification, I could just select my slabs, modify that selection, and under slab region I have the ability here to modify slabs under the same usage case. We're going to leave those set to 1 for all other components, but that's how you would attack that type of a change in the program. Now if I check a column and go to the release tab, you can see at the top and bottom there's no translational or rotational releases about the R or along RS directions. So we're going to just pin all of the columns at once. I'm just going to use select by type again. I'll do column. You have to be somewhat careful when doing this. For example, if I have a situation where I'm actually going to show this, let's go to this level, and I'm going to move this along this line to here. Let's do that movement, and then I'll insert a vertex here, and I'll just square that off like this. So this column here really becomes a double story or a double height column. If I go back to multi-level mode and let me check that in the rendering, you can see that condition right there. So if I select all of my columns, we'll select by type column, and we'll go back to modify the selection, and we can see under column we're going to modify the releases. So I'll release rotation about both axes, top and bottom. But what happens is that's going to create a hinge here. So when we analyze this, we'll likely get an instability. This column will just do something like that under the loading that we're going to apply. So I need to go back and actually modify that one manually. I'll take off the bottom rotational release, and then here I'll just take off the top rotational release here. Okay. Be aware of that. Make sure you correct any of those if you globally set the releases. Let's go ahead and save the model. And the next thing we're going to do is just apply a load to the structure, just a simple lateral load. We're going to use our seismic load wizard. I'll call this EQX. This is in the positive 0 direction. It does have some eccentricity associated with it. You can modify that as needed, and then we'll just use the default values here to generate an example set of story forces, and I'll apply that. I'm now going to go to load combos, and I'll add a combination. This combination, we're going to call this seismic X, and we'll say this is just 1 times EQX. Okay, the next thing we'll do is mesh the structure. So we'll mesh this. I'll use a mesh size, let's say of 5 feet, and if we're in multi-level mode, this will mesh the entire set of floors in multi-level mode. This now has been meshed, and I'll just go back to my default to turn off the shells that were created. It's now time to analyze the structure. So keep in mind that after releasing the columns, if we want to go back and fix those rotationally, we have to do that in a similar approach as to releasing them. The releases are not part of the actual usage case, so those manually have to be switched off and on. We'll go here to Analyze, Execute, and now I have the ability to determine which usage case I want to use for this particular run. So if I run this for, let's assume we're evaluating drift again, and I'm going to run this for crack 70 first, and we can now go ahead and run under the load case assigned. Once that's completed, we're going to go ahead and select yes to save the solution. It's important to note that while the program stores the reactions for every run that you make globally with each usage case, for example, if I run cracked 70, 50, and 25 successively, I can actually recall the reactions for each of those separate runs. However, the solution results that can be had here in the result viewer are only relative to the last saved solution globally for the structure. So in this case, when I go to analysis, you can see I'm able to review load combination results, for example, for cracked 70. Under load cases, which is shown here, this is where the program would allow the user to graphically review reactions, or you could also use these in different applications. Maybe we wanted to design a foundation with the reactions from crack 70 versus crack 25. Those can be recalled for application of reactions to a single level or a foundation system in Builder. But the load case option will then list and store all of the reactions for each usage case run. So this indicates that the reactions for dead load, uncracked global here. This is the uncracked sector. If I expand this then becomes the cracked sector. So this is actually the one that we had just run, cracked 70. You'll notice that this is really just default. We have not run uncracked number 1, and we don't have a solution for dead, live, or self-weight. To show that, if I just go back to columns only, and for example, I look at dead load for the uncracked case, go to analysis under columns, I could then select action dead load. This is the individual load case action. If I look at axial force, you can see nothing is shown because we don't yet have a solution for that. Again, that's just a placeholder, a default placeholder for this segment of this load tree. If I select EQX70, now that the analysis is done, it's important to note that the program stores only one global solution in its entirety at the time that it's run. So if I run cracked 70, that's the latest solution globally. If I then run cracked 50, that would replace that solution, and those solutions are actually stored in your model file under the building solution data. So this is the latest building solution stored here, and these ADO files contain different displacements, reactions, frame forces, etc. for the combinations or the load cases that have been solved under that particular usage case. The program does store reactions for every global run made. So if I ran the program for cracked 70, cracked 50, cracked 25, you would be able to access those reactions either graphically or through application of a single level rerun where you could then apply those reactions from any solved usage case. And you can see here under the result browser, for example, if I go to loads, there's two blocks here, and it's important to understand what these represent. The first block is for load combos. This represents the latest solution. So for crack 70, I have a set of combinations that I've evaluated. I've really only evaluated here seismic X, which is 1 times EQX. So that allows me to review results for the combinations that were solved under the usage case run. We also have a block here for load cases. That's shown here. And the only load case that's been solved currently is crack 70. So if I select that, you can see we ran EQX, that was the load case solved under crack 70. Crack 70 is a usage case, and its global G stands for the global run. If I reanalyze this for cracked 50, we would have a separate entry here for cracked 50 cases, EQX, cracked 50, G, and so on. This would just fill out this tree based on whatever load cases are solved for under that usage case. And the user can then graphically view results based on those actions. Now for load cases, the only thing we report here would be column and wall actions. So if I isolate columns, for example, I go over to analysis, you can see I have a result both for combination, which is whatever is selected in the combination list, or for action, whatever is selected in the load case list. And here we have EQX selected, axial force. This would show me then the axial forces for that solved EQX load case under cracked 70. Now if we go back to, let me just collapse that tree. We're going to go back to column drift. Now we have the ability to explore drift, for example, for walls. Actually, we want to go to wall drift. Let me go back to wall, and we're going to go here to deformations drift, and I'll isolate now walls only. So this result would then allow you to evaluate drift, and we kind of frame that as a reason why you may want to evaluate the system under different assumed cracking modifiers or stiffness modifiers. And you can see here just some of the drift percentages of each of the different wall levels. So this gives some output in terms of drift for these particular walls that were used as a primary lateral system. Now this, for example, if we look at these two top walls, this is 1.16, 1.04. If I just reanalyze the frame using crack 25, for example, we should see those numbers jump up where you have even more severe interstory drift percentage relative to the story height. And we'll run that and show that result. And then I'll also just go back and show that that gets stored under this option under loads and load cases. Okay, that one is now done. You can see that number jump up. Now we're looking at the latest result. So remember, this drift result is actually a function of just the load combination, seismic X. So that means that it's using the latest solution for whatever usage case we ran, which is the crack 25. And we can see those numbers went from 1.04, 1.16 to 1.58, 1.67. We could also look at displacements or deformations in the different directions here with these contour maps. If I looked at, for example, RR for this map, max displacement here is shown, and then here we have max displacement contours and values shown here as well. Coming back over to the loads, you can see now the crack 25 has been added. So if I go back to the wall actions, maybe I want to look at the shear along the strong axis, and having selected either crack 25, this is the reaction for that. Actually, let's go down here. These are the same because the load combination only includes the EQX case. But if I go to shear 25, you can see the distribution of shear through the wall. If I change that over to crack 70, you can see that number change based on that other solution for the stiffness modifiers. If you have any questions about the use of usage cases in Adapt Builder, please contact us at support@adaptsoft.com.